Okay, example 1, simulated gravity. Simulated we want 50% of G on this spaceship. Okay. There's a spaceship. I'm not going to draw anything else because it gets confusing, but if you're just sitting there in space, like, how do you get gravity? We just put this big mass out here somewhere so that if you're in here, you actually get stuck to the floor. Maybe put a little black hole there. Well, what about these people over there? Well, they're going to be on the wrong side, right? Which is fine. I guess this guy can live on this side, and these people can live on this side, but what happens if you want to walk to your buddy's house, right? Got a little bit of a problem. Anyway, you can't do that. So what do? We spin this thing. Give it some centripetal force to make it feel like there's gravity. And in this case, well, why spin it more than you need to? Because that takes maybe more energy to get it going. And it's actually easier on you if we don't have 9.8. Let's put it like maybe half that much. Okay? Be easier on your bones. Except when one day you came to Earth, then of course you'd be really, really tired for the first little while, right? You know, guys in space, they actually, astronauts, when they get back down to Earth, it's quite a shock for them, right? For their system, because they've been weightless for so long, and your muscles atrophy in no time at all. So they actually, when they even get to Earth, they just keep them there and don't even get them to try to stand up for a while. But even when they do, like, their muscles are shot. So what they actually do is put them on treadmills up in the space station. Have you seen pictures of Hatfield doing that? Yeah, resistance training, sure. But how do you even run on a treadmill when there's no gravity? You actually strap them down, right? They strap him down on the treadmill, have it go, and that way he has to exercise hours and hours a day, because otherwise you don't realize how much you're actually using all your muscles just by walking around. So anyway, we want to simulate just half of gravity on this spaceship. So what would be the period? And of course period is time. It's another way of saying time. Big T, little t, it's kind of the same thing here. How fast do I got to spin this thing in order to get half of what G is, which is 9.8 on Earth? Okay? What period is necessary? And let's say the ship is 100 meters. So if I said it's a 100-meter ship, what's that? Radius or diameter? Diameter. Right? If it's a 100-meter ship, I mean, if your car is 20 feet, if you got a 20-foot car, that doesn't mean from the center to the front bumper, right? We would assume. So, and we don't need that. So the first thing I want to do is go, there's a radius in my formula, that's what I want to do. Okay? So G is 9.8. I want 50% of that. 50% of G, that is 4.9. That's what I want for, and again, that's an acceleration. I want to feel that acceleration. That'll keep us all planted on the floors of this spaceship, and we'll all be happy. Okay? So how could I do that? I could, like I said, I could put gravity on this side. I could also tie this guy to a rope, couldn't I? I could provide that by tension, but we're not going to do that. I'm going to do that by spinning this ship. So I want to simulate gravity. So I want to make this guy feel like he's on the surface. And what do we call that when we have a surface? We have a force that's called, if this calculator is sitting on this table, we know it's got weight, it's got a normal force. I want to simulate a normal force, right? I want to simulate Fn. I want Fn to be 1/2 of regular weight. So 0.5 of mg. Okay, so what causes this normal force? It's caused by spinning the ship. But let's take it one step further. It's not just caused by it, it is the centripetal force. Okay? Yesterday we did questions with the car. And the centripetal force was the friction force. That was keeping it going in circular motion. Here the circular motion is just firing up some rockets on this thing, having to make it go, and then they can shut off, right? Like, what's going to slow this thing down? Nothing. There's no friction out here. So once you get it going, it basically can keep going like that until maybe something comes near and changes its direction. Okay, so normal force is centripetal force. 0.5 mg is mv squared over r. Okay, that's the concept. You got these formulas in here somewhere, but to get to that, you got to know this. So now at this point, 10 people would do this 10 different ways. So if it's not the way you would do it, you know, don't freak out. You would do something else. What am I trying to solve for here? Period, yeah. And we know that a velocity is a distance over a time, and this is basically the same time. Okay, we want like 1 revolution here, and you know you get questions where it's 10 revolutions and so on. Okay, period's just a time. So I could substitute that in there now. Okay, some of you guys would put in your numbers, and that's fine. Actually, what do I want to do first here? Yeah, can I, because I don't even have a mass in this question, do I? So let's do that. Let's make it a little bit nicer. 1/2 of g, I know that's 4.9, but let's just kind of leave it like that. V is d over, let's actually get rid of this r. Let's put it over here. So then I have v squared, which is 2 pi r over t. All of that is squared. I want to solve this thing for t, right? Okay. Like I said, you might do it some way differently. That's fine. Okay, so I got 0.5 g r is 4 pi squared r squared over t squared. Let's get rid of those brackets. Okay, let's divide by r squared. Let's divide by pi squared. Let's divide by 4. All right, and that's, I don't know if that was clever. That's 1 over t squared. Forget that. I don't want to do that. It's not the way. There's 8 ways. Well, you don't want to do it the 9th way, okay? I don't want to do that. Okay, let's cross multiply, right? I want t squared up there. Okay? Then I'm going to divide this stuff away. Okay? Yeah, I could have done lots of things. Yeah, I know. Okay. So t is the square root of all that stuff. Well, what's 4 over 1/2? 8. I got pi squared. I got r squared over r. So that's just r. All over, that's into there, g, right? Is that it? So, what do I got to plug in? I know what pi is. R is 50, g is 9.8. I want to take the square root of all that stuff, and if I didn't make a mistake, should be good. Oh, do I? Yeah, I got it now. Square root of 8 pi squared times 50 divided by 9.8 is 20.1. What's the units? What is this thing? Yeah, seconds. Sound pretty fast? That's what it is. It's not that big of a shit, really, 100 meters. Okay, so if this thing spins once every 20 seconds, I will simulate 4.9 meters a second squared. All right, so there's one question like that on there. Pretty practical question, isn't it? Remember, they just put someone on the moon just using Newton's laws. Back 50 years ago. Unless you're one of the people who believe it's a big hoax, it's a conspiracy. There's still some people out there like that. Okay. Example 2. Do they have any of these anymore? Or is it like the merry-go-round? They're just not safe. Kids aren't as smart as they used to be. One kid somewhere hung himself with a tetherball. Now they're banned from every school in the world, right? I'm serious. Stranger things have happened. We were just talking about this the other day. Back in the old days, you know VCRs? Old TVs, they were heavy. They had a glass tube. They were tube TVs. They shot electrons from the back of it, and it hit the phosphorus screen, and it glowed, right? And then they were black and white, just for phosphorus, and then they figured out how to get 3 pixels in there and make them color. Anyway, they weighed a lot. I bought a TV in the year 2000, which wasn't that long ago. It's a Sony XBR, 42 inches. It had 4 inches thick of glass, and it was actually modern because it wasn't curved, it was flat. It weighed 200 pounds. Okay, it was only that wide. It was deeper than it was wide. Anyway, they made these nice little, short little shelves, these little pieces of furniture where you put your TV on it, and your VCR went in a little cubby underneath, and underneath the VCR was a couple of drawers usually, or little drawers, cabinets, where you held all the VCR tapes, right? So little kids would come up and they would want to like turn on the TV, because you know we didn't have remote control. This one did, but years ago. So they would actually pull out the little drawer to climb up on top and do what they want to do on the TV. Guess what would happen when you pull the drawer out? Because this piece of furniture is only about 2 feet back. Yeah, the 150-pound TV would come and crush the kid. And you would think, oh my God, you read this in the paper, that's terrible. And then I saw a stat that said 3,057 kids in the United States last year alone died by this method. Yeah, and you're thinking, what? There's that many stupid parents out there? So the way they actually did was they made these straps that would go on the TV and strap it to the wall to prevent that from happening. But like, it's amazing. One little freak accident, you think, and then you read the statistic about how many, like America has 300 million people, right? So 1 in every, I don't know, 300,000 kids it happened to. Same thing with the tetherball. You think that would be like once, ever, forever. I bet you 8 kids a year died by getting strangled with a tetherball. Anyway, you guys do this, tetherball? You know what I'm talking about? Okay, you do. Okay, good. There's a tetherball. 25 degrees. And of course, the objective of the game is make sure you hit it at a nice angle whereby it swings over the other player's head in the other court, and you know he doesn't get to touch it, type thing, right? And I don't remember if you score points for every time you swung it around or what. So this thing's at 25 excuse me, degrees. It's got a 2-meter radius. Is that readable? Yeah, actually I want to cool it down, but thanks. Are they being noisy out there or something? So, what is the period? How long does it take when you hit this thing to spin around and you get it back again? Now we know the game, you would actually spin it at some angle up here. Okay, we're not obviously doing that. It's just going perfectly around at 25 degrees, which of course isn't possible. because the friction would slow it down and that angle would decrease, right? We have to take some assumptions. Okay, what's the first thing we should do? I'm going to explain this to grade 11s today too. Free body diagram. This isn't perfectly horizontal anymore, right? It's horizontal motion, but it's not perfectly horizontal. We got components. This ball, of course, has weight, mg. And what's the other force on it? What would I call this if it's tied with a string? Tension. Are there any other forces on it? Well, the tension is what's causing the centripetal force, right? The force of friction is what caused the centripetal force. So as far as the free body diagram, that's it. Now, having said that, we know that is what's causing it to go around in this motion. That's a component of the tension. That's the horizontal component of T, and that's the vertical component of T. Where is 25 degrees? Up here. So this guy, there's the right angle. This is a hypotenuse. Put T there if you like. That's the hypotenuse. This horizontal component is what? That is T. That's an opposite to 25, so that's got to be sine, right? So that is the component keeping this thing in its circular motion. Uniform. We just don't say the word uniform, right? This here would be then, that's an adjacent to 25, so that's T cos 25. So like I said, it's not really possible, but we're assuming this ball, when it goes around its motion, does it move up or down? No, which means that this force up has got to be equal to that, the force down. This is the component of tension up, okay? So vertically, T cos 25 has got to be equal to mg. That's the only two arrows we have in the vertical direction. Horizontally, if we analyze it that way, there's only one arrow. There's a net force here, right? It's not balanced like it is vertically. So that is T sine 25, and that is the centripetal force. Okay? The concept. So what am I trying to get? I'm trying to get the period. I just showed you a question where we're going to get a T in here, but I can't really solve this, can I? Because this T, and I'm sorry it's all confusing, that's not period, that is tension. I can't solve this. I've got two variables. But what can I do? I can make a substitution because I know tension is mg over cos 25. And if I put that in here for t, because that's t, then I'm going to have just one variable. Okay? So it's a kind of couple of steps we got to do. So let's go over here. So actually, let's go right under. So mg over cos 25, that is tension. That's called substitution, right? That's m over r. Okay, what's v squared? 2 pi r over t Okay, that's v squared. 2 pi r over t squared, distance over time. All right? So I was going to say there's only one variable in here I don't know, but actually, I don't know the mass of this ball, do I? Let's make something up. Do I need it? I don't, because m cancels out. So it doesn't really matter anyway, right? Let's divide both sides by m. You remember what sine over cosine is? Tangent. Oh, let's do that. What's sine 25 divided by cos 25? Tan 25. Why not? Okay, I don't want to pull a calculator out because I'm a big kid. 2 squared is 4. Pi squared is pi squared. R squared, over r over t squared. I can cancel an r out. Oh, thanks. Yep, there's a g there. Thank you. R cancels out with that. So let's just manipulate that for t squared again. 4 pi squared r, but r is 2 over g tan of 25. Okay, now let's pull out a calculator. Oh, make sure you're in degrees. I made that a 2. R is 2. Why? It's right here. Yeah, right? Square root of 4. Now again, most of you guys probably won't do it like this. That's fine. You'll put in a whole bunch of numbers. Just make sure I'm able to follow what you did in your work, right? Right, Reese? .1, and that's what I got before, so that looks good. Seem reasonable, kinda? I just made the question up, but kinda seem reasonable? 4 seconds? Okay, sure, right? It's not like an hour or anything. That's a pretty big radius though, isn't it? 2 meters? That ball is quite far away from that pole. So that thing's spinning quite a big distance, so it looks fine. Alrighty, that should be enough to finish that sheet, guys. And you should have only, what, 3 or 4 questions left? In about 20 minutes, I'll introduce